What's up, guys? Welcome to today's show. So, today we're going to try to finish our file compressor. And this far we have gotten quite far. We are able to parse a file and turn it into two lists. The first list containing blocks that repeat, and the second list contains mostly blocks which does not. So how do we continue on from here? Well, we want to use these two as use its indices, so we can replace the 32-bit blocks with 16-bit blocks. So that's the general idea. So let's see where we're at. We need to create some header for the entire file. So let's start there. So let's say we create a struct which we'll just call header. And what do we need to know? We need to know how many bytes the entire source file is. So let's say we have an int32 file size. We also need to know how big the lists are. But maybe, let's see here. Well, okay, let's do it like this. So we're gonna have an int16 containing the length of the first list. And what did we come to call these lists? Let's see here. Block list and the list tail. I think I'm gonna stuck with block list, and let's say this is the unique list. It's not quite certain that all of these are uniques. Hopefully they are not, because the more non-uniques, better. Let's also say that we have some magic string. So the magic string defines some thing which identifies this file type. So let's say we have 4 bytes for that. So let's say int8 magic 4, or let's make it 3, and then we add a revision or a version. So we know the version of the protocol in case we want to improve it later on. And then the file size and the 2 lists. And I guess that is all we need to know. So let's say typedef struct s header, and this is the header. Let's also create a constructor for this thing. need to know the, let's see, we need to provide the file length and the length of the lists. And the magic I will add statically. The version we can make a constant out of. So let's say version 1. And let's create this constructor. So we need a header. We need a size. The size is just the size of a header. And at this point we can actually assert that we have a P, because if we can't create the header, all bets are off. And let's zero out this thing. And now we just fill in the different values. So let's say P magic position 0 is a Z. And a Z. And a 0 byte. So this will identify our file type. The version we take from the constant. So we have the version, we have the magic. Now we go for the file size, and this we take from the argument. Same with the block list. And the unique list. And then we return P. All right, easy as pizza. So, let's see here. So let's go to our main 3, and we need to provide an output file here as well. But I think I'm not going to write directly to the file, but to some memory space. So So we get a little bit of flexibility. So let's say we have mem space. Okay, so we need to allocate for this mem space. And we don't know beforehand how big this needs to be. So let's try to figure out how big the maximum is. So for each let's see here. If all the blocks are unique, the file size is going to be 1.5 times the file size. So that's the worst condition. Plus the headers. So maybe we can do let's see, how are we going to structure this? Let's say we do mem space is equal to empty. And this is just a static size that we're gonna take care of. If we don't have a mem space, in that case we need to clear this out. And then we fail with a memory error. And return 1. So otherwise we have this mem space, and let's define that. And we need one argument because we need to know how big the input file is. So let's provide that. let's define the function. Okay, so let's see. So the size is going to be equal to the maximum, first the size of the header. And then the size of the two lists at its maximum size. So let's say we have size of in 32, and the maximum we can have is around 4,196. Then we have a second list at the same size, and then we have the file size so well, the file size, if we take into account the size of the two lists, the file size is still only going to be half when considering the data, since every 32-bit block will be swapped for a 16-bit index. So we can actually take file size divided by 2. And then we can add one 16-bit block just in case. Actually, let's make it 2. Okay, so this is our size. And now we can just allocate for this. If we don't have a P, we return an error. Otherwise, we return P. So now we have enough room for whatever it might be. Or should we provide the exact length of the lists? This is good enough. This is only a temporary storage area anyway. Okay, so when we have this mem space, what do we want to do? We want to copy over the headers and the lists into this mem space. And let's create some variable. Let's call this the offset. Then we want to call some function. Let's call them copy headers. We provide the mem space. We provide the main header. And then the two lists. And this copy headers function is going to return how many bytes we have used. So let's create this header first. Can't call it this. So the header is going to be equal to make header, and we need to provide the file size and the length of the block list. So blocks length and list tail length. Alright, so let's create this copy headers function, but we also need another utility function, which is some kind of mem copy, so we can copy memory. So let's first say we have a copy function, which is the memory copy. And it's going to take destination pointer, source pointer, and the size. And then we're gonna have our copy headers. So here we have the mem space. And what did we call these lists? Block list. So we need a block list pointer and a second block list pointer. What else? We need the header as well. Okay, so let's write these two functions. It should be fairly simple. Let's start with the copy function. So we have a destination, we have a source, we have a size. We need to have a destination pointer and a source pointer. We need to have some counter. So we set the destination pointer to destination, set the source pointer to source. We set n equal to the size. We're gonna iterate as long as we have an n, and at each iteration, gonna increase destination pointer, increase source pointer, and decrease the size. And at each iteration, we're gonna set value of destination pointer to value of source pointer. Easy enough. Okay, so the other function. This is gonna return an int32, copy headers. Gonna have an int 8 mems. Let's call this the destination. We're gonna have a header. We're gonna have a block list. Blocks and a block list uniques. Almost. Can we compress this just a little bit? Let's do this. All right. Okay, so how do we do this? First of all, we need to have some pointer which keeps track of things. And we need to know how far along we are. And then we just copy one thing at a time. I guess. Maybe we can have an intermediate variable as well. So let's start with a header. The size is size of header. And we set n equal to 0. P is equal to the destination. So we copy into P. The source is the header and the size. So then we increase P by size, we increase N by size. That's first. Now we need to figure out how big the blocks are, which is a pretty simple calculation. So it's just the size of in 32 times the block's length. So we copy into P, the blocks size. Then we take the next one. Same principle. This time it is the uniques. And that's all we need to copy. So now we can just return n, the number of bytes written. All right, we're getting there. So now that we have done all of that, we just need to parse the file and replace all the blocks in the file with the indices into our two lists. So we need to have some kind of a search function so we can locate something inside of our block lists. So what we want to return is the index, and that's an int16. So let's call this a block search. And we need to provide a block list. And the search string is going to be an int32. But how do we say if we don't get a match? Because index 0 is valid. However, we do have let's check what the maximum size of the individual lists are. So we iterate as long as items is less than 4195. Let me just double check that this is accurate. So let's see what the decimal of 0xFFFF is. No, that's not it. It should be this, 4095. But the list cannot be 4095. It can be 4194. And by the way, this is 4095. I'm glad I checked. So we need to put a 0 here. Let's search for all 41s. This could have turned into a disaster. I'm really glad I checked. Right. But as I said, we can return an error for this block search by returning this number, or this. Or we can actually make it bigger than that. Let's say this, because no list can be this big. So this we can most definitely use as an error case. Okay, so let's write this block search function. It should be pretty simple, I guess. So we need a block list. We need a, let's use the same wording as before. So this is our haystack, and we need an int32 needle. If we don't have a haystack, we return the error of 1000. So let's say we have some counter, do a for loop where we go where n is 0 less than haystack length, and at each iteration we check if the haystack blocks of n is equal to our needle. Maybe we can have a boolean as well. So if we find it, set found to true, and we break. And by the end here, we return. So if we have found something, then we return the index. Otherwise, we return this error value. And maybe we can make a nice constant out of it. Alright, something like this. So now we just need to parse through this file. So when we have copied the headers, we have an offset. Let's create a pointer. And this pointer should be equal to the mem space plus the offset. So now we want to parse the file. And what do we need to do in order to parse this file? What do we need to know? Well, we need to know the destination mem space, which is P. We need to know the source mem space, which is the file contents. What else? We need to know the two lists. So the block list and the tail. And let's give the header as well. Maybe in the other order. So we know for the file size and stuff like that. And we will get an offset back here as well. this copy headers, what does it return on error? Okay, it can't fail. Famous last words, right? Parse file, on the other hand, can that fail? Don't think so. Let's define the function. So in 16, by the way, did we have a 16-bit offset? Let's see here. Offset. It's in 32. Okay. So in 32 parse file, and we have a destination memspace, source memspace. We have headers. We have two block lists. And let's write this function, the most important function in the whole thing, but hopefully not the most complicated. So parse file, so we have an int8 destination, int8 source, we have some headers and two block lists. So blocks and uniques. There we go. Okay, so how do we do this? We need to have some int pointer and an integer. We need to keep track of the offset. We need to know how far along in the file we are. Let's see how we did it when we parsed the initial file. So that's the read file function. Okay, so here we just read in the whole files, and this was not what I was looking for. Read blocks is what I was looking for. So we keep doing this as long as n is more than 3. We set the n to the size, where the size is the size of the file, I guess. Is this correct though? So if it's more than 3, we continue. I actually think that we need to do one more iteration. Yeah. Since we're not dealing with negative numbers, I think the easiest way is just to set our size to something plus 4. And we can do a similar thing here. N is equal to the header file size plus 4. Offset is 0. P is equal to mem space plus offset, and we do this on P. But we are interested in the offset with regards to the mem space, not to P. So we should plus equals the offset here. All right. So I guess we need destination pointer and a source pointer. Alright, so let's do something like this. So n is equal to the header file size plus 4. Let's remove this. And we want to keep iterating as long as n is more than 3. And minus minus. Okay, so what we will do at each iteration, we want to set the int pointer to the current source pointer, and we'll set the integer to whatever is there. And we need some index. So now we have picked out one of these 32-bit blocks from the input file. Now we want to figure out in what list this is located. So the index is going to be search. What do we call this? Block search. So let's start by searching for it in the block list. And what we want to find is the integer. And if we get a match, so if index is not equal to no match, so this means we got a match in the blocks list, so the first list. Maybe we can wait a little bit with this. By the way, at each iteration, we want to increase the destination pointer by 2. And the source pointer by 4. Alright, so let's say we didn't get a match in the first list. Then we want to do another search, this time in the unique list. And now we must get a match, because every block is in one of these lists. If it's not, then something is really wrong. So let's say if index is equal to no match, in this case, then we can return a 0, indicating the error case. Otherwise, we have a match. And in this case, it's fairly simple. Well, in this case, we can just write the index to the current position in the file, in the output file. So we'll set the int pointer. Let's see here. We'll set the int pointer to the destination. And we write that index. Actually, we need a 16-bit int pointer. And we write the integer to the file. And that's basically all we need to do. And then the destination pointer goes 16 bits forward. The source pointer goes 32 bits forward. So this is the easy case. However, the more complicated case is when we get a match in the first list. Because then we want to also check how many of these blocks we have in a row. So how do we do this in an easy enough kind of way? Well, we want to count how many occurrences we have. So let's say we have some int 8 repeats. And we have at least one, so we can set it to that. So let's also set an n prime. And this we set to the current value of n. Okay. So let's set the int pointer to the source pointer plus. So source pointer plus 4. And we read in the integer. And we need to save the old one. Or let's do this, next int. And if the next int if it's equal to the current integer, then we want to increase the repeats. And we want to loop as long as the next int is equal to the integer. But we also need to increase source pointer to the next position. Starting to get a little bit complicated, this, but this is the last really complex thing we need to do before we have something which can compress a file. So the source pointer we add 4 to, and we go as long as next int is equal to the integer and repeat is less than 15. Because we can't handle more than that, because we're only going to have 4 bits to say if it's a to say how many repeats there are. So at this point we have have advanced the source pointer a few steps. So maybe we don't need to do it here. Which means we need to do it down here. Alright, so at this point we know how many we have read in. So let's construct our block to write, which is our output. So we're going to take our index and we want to make sure we only take 12 bits. And we want to OR this with the repeat counter. And here we're only going to take the least significant 16 bits of this. And we need to shift this over 12 bits. So here is shifted 0, 4, 8, 12. So by doing this, we can house both the repeat counter and the index in a 16-bit thing. So now let's write this. Like so. So let's see, we have if we get a match, we increase the source pointer by 4. Which means that it should be pointing to the next thing. But if we only find one occurrence, in that case we're still pointing to the current thing. So if repeats is 1, we need to advance it manually. Okay. I really hope this works because it will be a nightmare to debug. By the way, we also need to take this n prime into account because when we are checking for these repeats, we might go past the end of the file. So by the end here, we're gonna, by the way, we are taking 4 bytes at a time, so we need to minus equals this to 4. And same here. And we also need to check that the n prime is not, let's see, we're looping as long as it's more than 3. So if it's less than 4, in that case we need to break out of this loop. Okay, I think I got it right. What about the offset? Every time we iterate, we want to increase the offset by 2 because it relates to the destination. So by the end here we can return the offset and we know how many bytes we have written to that file buffer. Which means at this point here, when we have called this parse file, our mem space will contain the entire file, and our offset will contain the size of the thing. And since we allocated a whole lot for this, we can shrink that a little bit here. if we return an error, we need to handle that as well. And in this case, it's a parse error. So if we fail to resize this mem space, we need to end with a memory error. Alright, a monster of a function this, several screens long. Anyhow, now we know how big the file is, and we have the memory space for it. So now we can simply open this file and write it. So if we have some write file function which fails, we need to fail as well. So we need to provide the output file name, the mem space, and the offset. And this will be really easy to write. So write file, we have a file name, we have a mem space, we have a size, So we need a file descriptor, we need a sign integer for the return values, we need some counter and a pointer. So we open the file name and we open it as write only, and we want to create the file. And then we just do a for loop where we set p to the mem space, we set n to the size, we go along as long as we have an n, at each iteration we increase p and we decrease n. And we can write one byte at a time for convenience. Okay, that was no problem. So we write the file, we clean up, and we return 0. A lot of moving parts here. Let's see what the compiler says. Probably quite a lot to fix. Hopefully nothing complicated inside of our big function. Repeat undeclared. Repeats. Unique list undeclared. It's called uniques. conflicting types for main, that's true. Because now we have an output file as well. So we need to add that to our regular main as well. And when we are done with this, we're only going to take one argument, the file, and we're going to remove the ZZ at the end no, we're going to add it, right? Okay, so we don't need to change this here. So let's compile this thing. We need to calculate the size, and we need to have a variable for the output file. So we can easily calculate this by taking the size equal to the current size, the current length of the file name, and we add 3 to it. So now we can allocate the output file. We can assert that we have one. We can zero it out. And then we can just do an snprintf into the output file. Size -1. Maybe we can add 4 to it here. So size -1. And it's going to be the current file name .zz. So file name. And this is our output file that we pass to our main 3. Alright, so let's continue this after the break. Alright, you guys, so let's continue troubleshooting this thing. Let's see where we were. So expected expression before header 667. Right, this should not be header, this should be header abbreviated, like so. Output file, different signedness, that is true. We need to cast this thing to a char. Size may be uninitialized, is that so? Right, this should be size prime, so this argument right here. Alright, so now it's going to compile, but will it work? That's the interesting part, right? So let's see here. we have this file. Alright, let's run this on ls and see what happens. Okay, we got some output. So let's see if we create an out file, which should be called ls.zz. No, did not quite do that. Ah, .c, okay. +4. 1, 2, 3, 4. Maybe we need +5 here then. And the permissions doesn't look quite right. So let's see where we open this thing. This is the input file. No. This is the output file. So the third argument here is the permissions, but what is the format for it? So mode. Mode. The argument flags must include one of the following access modes. That's not it. Append mode. So the mode argument specifies the file mode bits to be applied. A new file is created. Must be supplied. The effective mode is modified by the process's umask. Okay, so we specify it like this. So what mode do we need for this? We want 0, 0, 6, 4, 4, I guess. But is this really the right format? Well, we'll see, won't we? Alright, so let's see what this output file is. So it's 21K big. So we need to find where the actual data begins. So let's see how our headers look. So the header contains first 3 bytes of magic string. So that's this. Then we have 1 byte of version. And we have the file size, which are 4. And then we have the length of the block list. So that's this. FF0F. So that means that the hex value is 0x0FFF. 4095. That makes sense, since the first part of this thing is the block list, which should fill up the entire thing. And then we have the unique list. So that's this, 527. So what we get is this value times 4, because each of these values are 4 bytes. And we have this times 4. Then we need to add the header size. So here we have 4 bytes, 8, 12 bytes. And then our other stuff should come. And if we turn this into a hex value, so 54A4 should be the first data part. So 54A4. So we look here, leftmost column, 5484, right? 54A4, okay. So here is 5410, 5400, 54A4. It ends here. So it did only do the headers and the lists, not the actual data. So why is that? So to this write file function we pass the mem space and the size. Mem space and offset. We should not give the offset here, should we? Or maybe we should, because the offset is the headers first. But then we run parse file and we add to the offset. So that must mean that parse file did not return, but it cannot return 0 because then this would have kicked in and we did not get a parse error, did we? Let's run it again. So let's see what the last message is. No, don't get a parse error. Now the permissions are correct. And the file name as well. And this is the size. Let's do something like this. Let's print the offset. At this point. And at this point. And let's not print all the other stuff. All right, let's see what it does. So the offset is the same. Right, I am comparing. I'm checking if the offset is 0. What's interesting at this point is if this function returns 0 or not. I think we need to create a temporary variable here. So let's set this return variable to parse file. And we check that one instead. And here we can print this one instead. So now we will probably see that parse error. Yes. Okay. So why do we get a parse error? Let's check this mega function. And what can make this return 0. Maybe we should have some sanity checking as well. So if we don't have a destination or a source or a header blocks or uniques, in that case we return 0. But we return 0 anyway, so do we have any additional returns here? Here, index no match. That's interesting. So we don't find that index when we search this integer. Let's add some printfs. So let's print the integer here, but let's also print it here. Maybe it changed, and that's why it doesn't work. And this too should be the abbreviated header. Okay, so we run this a lot of times, which means that it works. And it is the same in both these occasions. But we get a parse error at some point. So this value is not found. Command substitution, ignored null byte in input. Can we grep for something binary? Yes. Binary files is equal to type. So what's type? Maybe we can just specify this. -C, what is that? Output 0 bytes instead of the character that normally, no, that's not it. Null data. So let's see. Let's try Z first. This. So how can we search a file? Maybe we can just do a hex dump of ls and grep for 4011. So where does that 4011 come from? So let's see how we can do this. Alright, so this seems to be working. So let's remove this head. Okay, so here we have the hex for the entire file. And what did we want to search for? Let's rerun the command. If I can find it. Okay, so let's first check for let's try without this LFS stuff. And let's grep for this right here. So 3B 83 EC00. Okay, got a match. So what about 1140? 0000. We do get a match. Okay, we probably need to enclose this. So let's search for this again. And then 1140. So we search for this string. No match. Did I get the order wrong? So 00 EC 83 3B. No. 1140 00 00. Let's try taking something from the top. So we run this and we run head. And let's pick this one. And let's provide it in both orders. So 7F 45 4C, 46. Not found. Not found. Okay, that's weird. So let's see here. So we set the source pointer to source. And we set this to the source pointer. And then we grab the integer. So what is this source? If we go to where we call this parse file, so the source is the contents. And the contents we get from read file. Do we use this content anywhere else? We read the blocks. So we read in this. And if we hex dump the input file and check the beginning, so we have 46, 4C, 45, 7F, 46, 4C, 45, 7F. And what do we have in the beginning of this dump? 45. Let's copy this first stuff. Seven F. So they are swapped 2 bytes at a time. Weird. Okay, so this reads in. Okay, I see. Mm, 2 bytes. What if we do -C? Small c. Okay. Weird that we can't just do like -big C canonical. Display the input offset in hexadecimal, followed by 16 2-column hexadecimal bytes, followed by the same 16 bytes in %p format. Because I want this format, but not the extra stuff. We should be able to specify our own format. would be helpful to see some examples. Okay, here. weird. Oh, okay. We're starting to get there. Okay, so this prints characters. Hmm. One, 2, and 4 byte count support. byte count or field precision. There we might have gotten it. Alright. So let's see if we can find this string. So here we have it in this order. And then we have 4C, 46, 7F, 45. Alright, it's not going to work this way. We need to search for it in 2 byte at a time order. So let's save this and this, let's say. And let's grab the first one. The first integer is what we want to grab. This one. So let's take this as an example. If we want to search for this one in our file, what we're going to search for is, instead of 464C, it's going to be 4C46. And same with this this part. So instead of 45 7F, we're going to have 7F45. So this string should be found in our file. Four C 46. Okay, so we need to reverse these 2 bytes as well. So if we want to find this, so we start with these ones, so 7F45, and then these 4C46. Then we get a match, all right? So let's now see if we can do the same with the second to last one. So we start with the right part, which is 3B83, and then EC00. Do we find this one? No, we don't. And what about the other one? This one right here. So 1140 0000. It's there. So why don't we get a match in our list? And why didn't we find the other one? Maybe I did something wrong. Let's try this once more. So 3B83 EC00. It's weird that we don't find this one. It's like we have read in 1 byte less than what we should have. Ah, right, we pad it with the zeros. That's right. That is right. Okay, so now I think I know what might be wrong. We are going too far in this file. I don't think we should do file size +4. Which means we probably shouldn't do it here either then. Well, here we probably should. But there is another function. So in addition to these parse files, it's block something. Parse block or read blocks. So here we do size +4. Don't think we should do that actually. Let's see what happens if we do it like this. We still get a parse error. But that's because this is padded and our file is not. So how should we deal with a block when we get to this padded byte? Let's see what happens temporarily if we just ignore that parse error silently as a temporary thing. So if we don't get a match, instead of returning 0, let's say we're done. Okay, so now we did not get an error. And the file is smaller, but is it too small? We still don't. We still don't return the right thing. Because we only write the tables. So these are the bytes that we should write after the headers. So why don't we? Okay, I forgot to add it to the offset. Okay, now we should have some data. So this is still the size of the header. No, is this the size of the headers? So 54A0. A0. So from here we are dealing with the data. So this right here, 1301, that should be an index. Thirteen oh one. Right, so 1301. The one in the beginning here indicates that this should repeat one time. So the index is actually this. So let's see where we can find this index. So this should be found, let's see, in the first list, I think. So let's show blocks at this index. Well, it should be blocks at this index. So if we have done this correctly, this should refer to the first 4 bytes of the file, of the input file. see what happens. So it's equal to this right here. And if we hex dump our input file, so we have 7F 45 4C 46. Okay, that's really nice. So that part seems to be working. So that's from this index right here. And then we have another 13. So that means that there's still one repetition. Here though, we have a 2, 2 0 0 0. So this should indicate that we have 2 repetitions of index 0. So first we have one string, then we have another, and the third thing in the file should be a repetition of the first index. So first we have this, then we have this, and then we have all zeros. 1 integer, 2 integers. It is actually working. So we replaced one consecutive repetition block. Okay, it works. That's cool. Let's see if we find something from the other list, which means it should have repetition set to 0. So here's a 1, here's a 1, here's a 2, a 1, 1, 1, 1, 1. There must be some unique block somewhere, right? Here's a repetition again. And here we have 3 repetitions. And here's 2. But we don't seem to have any 0 repetitions. which is pretty weird. We should have a lot of these. Here we have a lot of zeros, like every other one, but it's the wrong byte. But maybe these are just a lot of 0 bytes. So according to this, we never hit something which is only in the second list. Oh, wait a second. We set the output to the integer. We should put the index here. That's right. And maybe that's why the file turned out to be so big. Okay, that's better. It became a little bit smaller, but still not small enough. So let's see here. Let's go down to 54A0. Here we have 1 repetition, 2, 1. I still don't see enough zeros. So let's see if we get any of these messages. Okay, we do. Quite a lot, actually. Let's print the offset as well. Okay, let's see what we get. Alright, so let's check this offset. 3FCA. Right, we need to add something to it. We probably need to add this to it. Because we need to use the offset in relation to the header size as well. Alright, so at offset 94 6A. '94 6A. So this is 6. So this is 0. This is 7. 8. 9. 10. Okay, we are having some trouble with the end of the file. Maybe I should take something else. Let's see if we can take something in the beginning instead. So 70FC. F 70F. What did I say? 70FC, right? So this is 0. This is 7, 8, 9, A, B, C. Right, so this is a 0, 0. Which makes sense since this is the first in the list. So, okay. Do we have any more of these? Here's another one. And here's one. And here. Okay, seems to be working. We need to fix the end of the file though, because there's some trouble there. But the rest seems to be pretty okay. I'm a little bit worried though, because the file did not did not really shrink. What if we compress something else? Not a program, but some text file maybe. What about some config file? Let's say protocols. It's 68 lines. How big is it in bytes? 3000. Oh, that could be it. Okay. So let's begin by copying this file here, and we run cc on protocols. It still grows. Why? So these 4 bytes are the magic, etc. And then what do we have? 4 bytes of file size. So that's this. Then we have 2 bytes of the block list and 2 bytes of the unique list. So the block lists is this big, and we don't even have a unique list here. So it should definitely not be bigger. How can it even be? So this is the number of entries. $638 entries. So 2,500. So the data should start at 0A04. Zero, 1, 2, 3, 4. So here. So this is 1 repetition, this is 1, this is 1. Okay, so it's not really a lot of repetition in this file. What file could we use if we want to find repetitions? Let's artificially create some weird file. So it's 8K. This actually got smaller. Half. What would happen if we were to compress this file again? This time it got really small. That's interesting. So maybe we should make an iterative process of this. Does this work on the LS as well? Okay, it's too big. Let's take half of it. So Let's run cc on this ls2. And on the compressed file. And again. So we went from 16K to 18K to 27 to 40. So no, that did not work on that file. What about protocols? I think this might actually work better. So we went from 3K to 4K to 6K to 8K. It did work very well on this artificial file though. But it's not really a point if we only need to, if it only works on files like that. We need to think a little bit and see if we can optimize this more. But one good thing is that all we intended to do is working at least. So we need to fix some small bugs and maybe optimize the algorithm a little bit. But I think this will be all for today. I really hope you liked this episode. Please like and subscribe, and thanks for watching. Thanks for today.